Hello everyone, I'm Yeonong Park, a PhD student at Seoul National University. In this talk, I'll be presenting a work titled Graphene, Strong Yet Lightweight Rollhammer Protection. This work is done with my colleagues at Seoul National University. I will begin with a brief introduction on rollhammer phenomenon. Rollhammer is a phenomenon that repeatedly activating a certain DRAM row causes the bit flips in its nearby rows. The rows being repeatedly activated are called aggressor row, and its nearby row affected by repeated activation are called victim rows. Such a vulnerability can be exploited to realize various severe system attacks. To materialize rollhammer attacks, hammering should be done in a very short time, as each row gets refreshed every refresh window. And we define the minimum number of activation causing a bit flip within the whole chip as rollhammer threshold. Since the public disclosure of rollhammer, there have been years of efforts to mitigate this problem. Intel proposed a memory controller supporting target low refresh. In 2016, DRAM vendors announced they include in DRAM rollhammer mitigation mechanism in their products. Also from academia, many works have come out. So is rollhammer still a problem? Despite such an effort, unfortunately, the answer is yes. Very recent experimental studies demonstrate that even the latest DDR4 DRAM chips are susceptible to rollhammer attacks. Besides, rollhammer threshold has reduced due to technology scaling. For DDR3 chips, rollhammer threshold was more than 100K. Now for DDR4 chips, rollhammer threshold is only around a few tens of K. Such trend is highly likely to continue. So it is reasonable to presume that DRAM chips with sub 10K threshold would come out in near future. Previous countermeasures are not scalable to reduce the rollhammer threshold. They incur too much area, energy, and performance overhead. We need a new solution. So we propose Graphene, a low-cost counter-based rollhammer mitigation scheme exploiting a space-efficient algorithm that identifies frequent elements from a data stream. Graphene guarantees to protect the system from any possible rollhammer attacks and features very low energy and performance overhead. In addition, Graphene incurs very limited area overhead. Finally, Graphene scales gracefully with a reduced rollhammer threshold. Now I will explain how Graphene works for rollhammer protection. An important question to answer is how to identify potential rollhammer with high precision and limited memory. The key insight is that we can formulate the problem of detecting rollhammer attacks as frequent elements problem. Frequent elements problem is to find items that appear more than some fixed fraction of the data stream. Meanwhile, detecting rollhammer is to find rows that are activated more than some threshold within a refresh window. There is very strong similarity between these two problems. Since frequent element problem is a decades-long problem with many well-studied solutions, such framing allows us to exploit the fruits of decades of past research. For aggressor tracking, Graphene uses Miser-Gris algorithm, a space-efficient solution to frequent elements problem. Miser-Gris algorithm maintains an associated array data structure called counter table. It has item ID as key and estimated count of the corresponding ID as value. In the context of rollhammer, item ID is a row address. Note that the count field of the table is not the actual count of the corresponding row address. This is why we call this estimated count. On top of the counter table, Graphene also has special register called spillover counter. Before explaining how Miser-Gris algorithm works, I would like to emphasize what this algorithm guarantees. Miser-Gris algorithm identifies all the items that appear more than t times in a stream of length w. For this guarantee, the number of counter table entries should meet this condition. This is a flowchart of the aggressor tracking of Graphene. I will explain how it operates by giving an example. Here is a counter table with 3 entries. Every time an activation comes, the table as well as the spillover count are updated according to the activated address. First, the row 1010 is activated. Since 1010 is in the table, it increases the matching entry's estimate count by 1. Secondly, row address 4040 is activated, for which there is no matching entry. Also, no entry has the same count value as spillover count, so it increases spillover count by 1. Lastly, a row address 5050 is activated. Again, there is no matching entry, but in this time, the third entry has the same count value as spillover count. Thus, we replace the address of the third entry with 5050 and increments the count by 1. Now I will explain how Graphene exploits this powerful tracking algorithm in the context of rowhammer protection. First, Graphene restarts tracking by periodic reset of all the tracking information. This is because Misragri's algorithm only applies to a finite stream. However, a sequence of activations is not necessarily finite. Therefore, Graphene performs periodic reset, and it enables tracking algorithm to work on a finite stream of activation. The number of activations that can be issued within a certain amount of time is limited by DRAM timing parameters. In this way, we can conservatively set W, the length of a stream to track, as the maximum number of activations that fits in a reset window, considering the worst case. And to thwart attacks, Graphene issues victim row refreshes when an estimated count is specific threshold T, or a multiple of T. This is a visualization of how Graphene works with the tracking information. We assume T to be 10K. When it resets, Graphene makes row address fields empty and initialize estimate count and spillover count to 0. When any entry's estimated count is T, it issues victim row refreshes. In this case, the entry with the row address 1010 is the one, so it issues victim row refreshes for the row 1010. As another entry's count is T, it again generates victim row refreshes, and this time for victim rows of 2020. And it resets again as new reset window begins. After a sequence of activation, in this time, it refreshes victim rows of the row 3030. The 3030 has been repeatedly activated even after the first victim row refresh, so its count eventually reaches 20K. In this case, it issues one more victim row refreshes for the row 3030. By doing so, Graphene prevents any row from being activated more than T times without generating victim row refreshes within a reset window. Please see the paper for the proof of this guarantee. What Graphene guarantees is that no more than T activation on a single row can be made without generating victim row refreshes within a reset window. Then how to achieve complete rowhammer protection with this guarantee? Configuring parameter T, which is a threshold for victim row refresh, is a key. Intuitively, T seems to be a function of rowhammer threshold. However, we should not naively set T same as rowhammer threshold. Instead, we should address two issues carefully. First, two aggressor rows can concurrently disturb a single victim row. It means that activation as many as half of rowhammer threshold on a single row can cause rowhammer in the worst case. As Graphene tracks aggressor rows, not victim rows, we should take this issue into account. Second, Graphene's guarantee is established within a single reset window. However, activations can accumulate across multiple reset windows. Let's assume that a victim row of row X is refreshed here and here. The interval between these 2 points would be TRFW, which is a refresh window. As can be seen here, this interval of TRFW can stretch over multiple reset windows. During each reset window, up to T-1 activations on row X can be made without victim row refresh. It means that the row X's victim row can be disturbed far more than T times between its 2 consecutive refreshes. This issue also makes T much smaller than the Rowhammer threshold. Here I am summarizing the parameter configuration of Graphene. The Rowhammer threshold of 15K and a reset window of TRFW are assumed. W, the maximum number of activations in a reset window. Assuming DRAM timing parameter, shown in this table, W is 1360K. T, a threshold for victim row refreshes, is determined by this inequality considering the issue mentioned in the previous slide. As the Rowhammer threshold is 50K, T is 12.5K. The number of counter table entries is automatically set according to this inequality as W and T are settled. Consequently, only 108 entries are necessary for each bank to completely mitigate Rowhammer attacks. You can find details in the paper on how to extend Graphene for non-adjacent Rowhammer. So far, we only assume adjacent Rowhammer. Also in the paper, you can find a way to further reduce counter table size by adjusting reset window. Now I will explain about Graphene architecture. We suggest to locate Graphene at a memory controller. However, this decision remains an issue. Current DRAM protocol lacks a pulse for memory controller to issue a refresh to a specific row at a specific time. So we introduce new DRAM command named nearby row refresh. Whenever victim row refreshes are necessary, Graphene sends alert signal to memory controller. The memory controller sends NRR commands to DRAM, making it perform refreshes for physically nearby row of the aggressor. For each NRR command, the bank in question stalled as much as the number of rows to refresh. You can find details on counter table implementation in the paper. Now let's move on to evaluation and conclusion. We compare Graphene with the 3 prior schemes, Para, CBD, and Twice. We perform a cycle level simulation to count the number of victim row refreshes and their impact on the system performance. This table is a detailed simulation setup. We use both normal workload and synthetic workload to mimic possible adversarial attacks. Here is description on the workload we use. This is the result. We evaluate area energy and performance overhead of the 4 schemes, reducing the Rowhammer threshold from 50K to 1.5K. Across all Rowhammer threshold, Graphene features relatively low overhead in terms of area, energy, and performance. On the other hand, the other schemes incur significant overhead, at least in one aspect. Twice table size becomes impractical with the reduced Rowhammer threshold. CBT and Para incur significant energy and performance overhead, which increase with the threshold reduction. You can see additional evaluation results and discussion in the paper. So this paper proposes Graphene. By exploiting a highly efficient algorithm, Graphene provides protection guarantee with tightly bounded energy, performance, and area overhead. Such Graphene can work as a scalable solution to reducing Rowhammer threshold of modern and future DRAM system. Thank you for listening.